Hello, my name is Leo Fernig and I'm one of the volunteers with the Star Notes project. I think I've been working on the project since October 2020, and this presentation is about a little side project I did using one of the notebooks of Mollie O'Reilly. I think we are transcribing the notebooks of Mollie O'Reilly in June and July 2021, and the one that interested me particularly was phaedra1056, that has a number of measurements of RW Monocerotis, an eclipsing binary. The star was discovered in 1907 at the Moscow Observatory by Lydia Saraski. If we turn to page 176, we see the first of a set of measurements. You can see the plate number AM2295 with a magnitude estimate of 8.7, and then the next plate with another magnitude estimate, and so on and so forth all the way down the page. It looks like this project went on for about 5 weeks and took the last 3 weeks of May and the first 2 weeks of June. Mollie O'Reilly filled a total of 20 pages, and it looks like she examined about 230 plates. There are a couple of other interesting things in this part of the notebook. One page which looks like an attempt to establish a comparison sequence, and for that comparison sequence it looks like 3 MC plates were used, and if you look down at the bottom left hand corner there, she's calculating the mean magnitude of the comparison stars across the 3 plates. There is also a graph in this section of the notebook which might also be the means of the magnitudes of the comparison stars. Well, the purpose of this exercise was to actually use Mollie O'Reilly's measurements with a Lightcurve analysis tool, and I've been using V-Star, which is the AAVSO's Lightcurve analysis tool. And in case you're interested in it, you do need to have Java 1.8 installed on your machine, but it is free and open source software. Well, the first step before using V-Star was to get the measurements into a file that could be ingested by the tool, and that really is just a comma delimited file with the Julian date and the magnitude. Just FYI, in order to get the Julian date, I wrote a little Python script to scrape the dates off the plate search database. So now let's examine these observations using V-Star. When we open V-Star, we have the option of either downloading observations from the AAVSO database or from opening a CSV file. And here are observations of RW Mon. And if we look at it, it doesn't seem that there's an obvious light curve, so let's do a phase plot. So under Analysis, we can select Phase Plot, and the first thing it does is ask us for a period, and unfortunately we don't know the period, so let's go to the AAVSO's VSX variable star index and look for the period of RW Mon. Okay, and there it is, 1.906, and let's paste that into V-Star. Here we go, and say OK. And that looks a bit better. Now we can see something that looks a little bit like definitely the eclipse of an eclipsing binary. Just to make the thing a little clearer, let's do a polynomial fit of degree 30. Might look quite nice. And there you can see the curve. You can clearly see the eclipse here. And I was wondering if this here actually might be the secondary eclipse, but that would obviously require a lot more analysis. Now the problem is, of course, we kind of cheated. We assumed we knew the period, so let's backtrack and see if we can discover the period using V-Star. So let's load up the data again, and starting from scratch. So new star from file, RW Mon, open. And we're going to go to analysis, and we are going to do a data compensated discrete Fourier transform search for a period. It's going to ask us for a boundary within which we're searching for the period. I'm going to say anywhere between 0.5 days and 3 days. And with a resolution, this applies to the phase. And say OK. And there's clearly one period that stands out here. And if we go to top hits, we will see that that period that stands out the most is 1.906 days. And we can go to phase plot directly from here and see the phase plot, which is quite good. I don't think it's quite as nice as the one from the more recent period that we got from the AVSO database, but let's look at what it looks like with a polynomial fit of degree 30. So yeah, again we can see very clearly the eclipse happening here at the bottom of the light curve. Lastly, I thought it would be really interesting to actually see RW Monocerotis. So here it is on an AAVSO finder chart from their variable star plotter. And here it is on a DSS image rendered by Aladdin. Well, for me, this exercise raised a whole bunch of questions. First of all, whose idea was it to make these measurements, and who assigned it to Mollie O'Reilly? Was it Annie Cannon? There are other hints in the notebook that she was the sort of de facto supervisor of the computers at this time. The second question is, how exactly did Mollie O'Reilly arrive at these estimates? Was it just eyeballing the plates? Did she use a fly spanker? Was the comparison sequence used to calibrate a fly spanker? Then I wondered, what were these results used for? I couldn't actually find an article in the literature based on this particular set of measurements. And the period of 1.906 days had already been established before these measurements were made. Lastly, and the one that really interested me, is how close are these measurements to those of the automated dash photometry? The two sets of numbers are clearly related, but it requires, I think, a little more analysis. A lot of Mollie O'Reilly's estimates seem to be a little on the bright side. She has a lot of measurements that are 8.7, which is quite a bit brighter than the 9.2, which is usually cited as the maximum of the brightness of RW Monocerotis. And I was wondering, is this maybe a consequence of the photographic emulsion? Anyway, those are the questions I had. I hope you enjoyed this presentation. Thank you.